Part 2 and Part 1, we said that the behavior of an ideal gas can be described using a pressure versus volume graph. We introduced these four ideal gas processes. We explained them with PV equals nRT and the first law of thermodynamics. We even showed off a little bit, especially with the adiabatic process and the isovolumeric process as they cycled around in the internal combustion engine, and that was fun. We also have isobaric processes and isothermal processes. We love you guys too. And we believe that the work done by this process is equal to the area under the pressure versus volume graph. And we see the connection here with the heat engine that we mentioned earlier, but this is all too qualitative. We want to put some numbers to this thing, and we also want to connect the internal combustion engine with our old friend the water wheel and see how heat is the flow of energy due to a temperature difference. That will be the challenge for this video, so let's get to it with this big question. How can we compare the change in thermal energy, heat, and work in each of the following two cases, case 1 and case 2? In each case, we have 0.05 moles of a gas. Pi, Pf, Vi, and V final are as listed there, and we have a lot of numbers here for case 1 and case 2. Case 1, as you can see, takes the low root. Case 1 has isobaric cooling and then isovolumeric heating. Case 2 has isovolumeric heating followed by isobaric cooling. And you see the numbers there, but I should point out that a 12 meter cubed, a cubic meter is pretty big, so a 12 cubic meter cylinder is kind of ridiculous. We're trying to keep the numbers user-friendly, if nothing else here. 18 pascals, I should also point out, is an incredibly small pressure compared with atmospheric pressure. Regardless of all that, PV equals nRT, still a true fact. Remember that n is equal to 0.05 in all these cases. And why am I bringing PV equals nRT into this situation? Well, because if you look at those values, you look at these graphs, we know pressure, we know volume, we know R, we know N, we can find T. 1, 2, 3, 4, 5, 6 times we can use that equation, and notice that we only get, however, 3 different temperatures. Clever. We chose that 6 times 12 is equal to 18 times 4, so both case 1 and case 2, if you add the steps together, give you an isothermal process, although we are not following that nice curve, that hyperbola, which is the isothermal line. We're doing this in 2 different steps just to be a little bit trickier about it. But good for us. We used the ideal gas law to do something. We found these temperatures, and if we know temperature, we can use this equation, 3/2 nRT, to find these values for thermal energy. And there they are. You can check my math, but I think we're good. And now we know everything we could possibly want to know, because at each of these locations, we know the temperature and the thermal energy. For case 1, cool off first and then get back to your original temperature. For case 2, you get to a higher temperature first and then get back to your original temperature. So we know everything we could possibly want to know, except we don't, not yet, although we can figure it out. We can figure out more about W and Q. W and Q will do the isovolumeric process first because that's easier. Why is it easier? Well, because delta W equals 0. For an didn't you pay attention to the last video? Delta W equals 0 for an isovolumeric process, and there it is. And what is delta E and delta Q? Well, look at the sheet. Delta E and delta Q both have to be 72 joules. They have to equal one another because of the first law of thermodynamics. And looking at the blue values there, 36 plus 72 is equal to 108, 108 joules. And we're moving on to the more difficult one, the isobaric compression. Isobaric compression. From the previous video, we know these facts about isobaric compression, and we'll take them a little bit more slowly this time. First, delta E. Delta E has to be negative 72. That's right, negative 72 joules from 108 down to 36. What about delta W? Delta W is 48 joules. Now, why is it positive? We know it's positive. A positive value for delta W because we are going to the left. We are compressing this gas. We are doing work on the gas. We know it's 48 joules because of the area under that line. 6 times 8, between 4 and 12, that's 8 meters cubed, times 6 pascals is 48 joules. So now if delta E is negative 72, delta W is 48, that means delta Q has to be negative 120 because, first law of thermodynamics, Delta W plus delta Q is equal to delta E, and there we have it. Now we can say we truly know everything that we want to know about case 1, and we can move on to case 2. Case 2 is very similar, only different. In case 2, we'll start again with the isovolumeric heating, and again we know that delta W is 0. What's delta E for isovolumeric heating here? Well, with the power of subtraction, we can find that the value there is 216 joules. That's delta E, that's delta Q, that's the amount of heat energy you have to pump into the system in order to get it to that intermediate state. And now we are isobaric cooling, isobaric cooling. Let's do this one at a time again. Delta E, what does delta E have to be here? Delta E has to be negative 216 joules from 324 down to 108. Okay, what about delta W? Delta W has to be positive 144 joules. That is 18 times 8. Again, the area under that blue horizontal line, it's to the left, so delta W is positive, and that means delta Q by the first law of thermodynamics must be negative 360 joules. And now we truly know everything that we'd want to know about case 1 and case 2, and we can add them up. We can add up delta E, delta W, and delta Q for the 2 steps, and there we have it. And what do we have? We have that both of them didn't do anything. They didn't do anything. When you add the 2 steps together, they didn't do anything in terms of delta E. You start with the same thermal energy in the gas. You end with that same thermal energy, the same temperature from beginning to end. But what did case 1 do? You put in 48 joules. You flexed your muscles and exerted 48 joules of work into that system, and the system put out 48 joules. These things feel hot. Now you're looking at me and you're like, well, that's not true. I see it on the sheet there. Delta Q is negative 48 joules. And how can you say this thing feels warm to me? Well, why does it feel warm? It feels warm because it's putting out heat. It's pumping the Q into U's. From the gas's point of view, it receives a check in the mail. That's nice. It receives the delta W and it gives out the delta Q. If you touch a hot burner, and don't do this, or a hot radiator, don't do that, and it feels hot, that's because it is losing heat into your hand. Don't do that. What about case 2? Case 2 is the same sort of thing. You are putting in work and you are getting out heat. The gas gets your work, thank you very much, and gives you out heat. The only difference between case 1 and case 2, these are both heaters. Case 2, it turns out, is on a higher setting, putting out more heat, taking in more work or more energy. You could say it's taking in more electric energy from the power company and putting out more heat, even though the temperature of the gas stays the same. Now you're thinking to yourself, this is all very interesting. What does this have to do with an engine? Nothing so far until I do this. See what I did there? I switched them around. The case 2 got switched around. It used to be that, and now it's this. It got switched around because now I can do that. And now we have a cycle. Now we have a cycle that can go on and on and on and on and on again. Just like something else that reminds me of. No comment. Anyway, here are our 4 different parts of this cycle. Again, it's isovolumeric and isobaric, and it's got delta Q values, and we can add up the heat put in. 360 plus 72 is 432 joules of heat that need to be put in during those 2 stages, and QC, the heat removed, is 336 joules, and this engine does 96 joules of work, and we are happy. We are happy about that 96, and I'll tell you why we're happy. QH is equal to W plus QC, which has to be true. Has to be true that QH is equal to W plus QC, and also we are happy that if you look at it, 96 joules is equal to the area of that box. The area of that rectangle there, what's our total? We've got 12 on the vertical side, and then we've got 8. 12 times 8, 12 pascals times 8 meters cubed is 96 joules, isn't it? Units, check out, yeah? Yeah, all right, we're good, and we can tell you something more. We can tell you that this machine is 22% efficient. This engine, 22% efficient. Efficiency, what you get out, 96 divided by what you put in, the 432 joules. And that's your efficiency, and that's the last thing I wanted to say about engines. I wanted to return to talking about water wheels, and I want to refer again to water as this invisible fluid, and I want to talk about heat as the flow of energy due to a temperature difference. Just like the water wheel has the flow of an invisible fluid called water doing work due to a height difference. Heat is the flow of energy due to a temperature difference, and heat flows from hot to cold. Just like water flows from higher to lower, heat flows from hot to cold. And what does that mean? It means if you take hot water and cold water and you put them together, you get out warm water. You get out warm water. Now that is heat flowing from the hot water to the cold water. Heat flowing from the hot to the cold. And the equation for this flow of heat is Q equals mc delta T. That's the key equation, and that relies on heat and temperature. Think about that equation, heat and temperature being totally different. Temperature, what is temperature? It's a measure of hotness or coldness. Heat is the flow of energy due to a temperature difference. Heat and energy, different things. Q and T, not the same. Joules and Kelvin, not the same thing. Or consider a piece of metal being put into some water. But before we do that, we'll put the piece of metal to a flame to raise the temperature way up high and then put it in the water, and the water will get warm. Several things about this. Number one, the final temperature of the water and the final temperature of the metal have to be the same. They have to be the same. Why? Because heat flows from hot to cold, and heat will continue to flow until they reach the same temperature, called thermal equilibrium, because that sounds smart. Anyway, that's true. The heat lost by the metal is losing heat to the water. The heat lost by the metal is equal to the amount of heat gained by the water, but that doesn't mean that the temperature change is the same. We expect a really big temperature change for the metal and a much smaller temperature change for the water. And if you make any steam, that's an added level of complexity, which I choose to ignore. Q equals mc delta T rolls off the tongue, just like PV equals nRT. What is this C, though? C is the specific heat capacity, which is the amount of heat energy needed to raise the temperature of 1 kilogram of the material by 1 Kelvin or 1 degree centigrade. And if you're talking about a change in temperature, the absolute temperature, K, and degrees C are different. But if you're talking about a change in temperature, you could talk about one just as soon as you could talk about the other. For this example here, with the hot metal and the cold water, water has a really big C and a smaller delta T. The metal has a smaller C and a bigger delta T. But again, I repeat, conservation of energy. The heat lost by the metal is equal to the heat gained by the water. But enough about water, back to gases. Here we have a wall between a hot gas on the left and a cold gas on the right. Hot gas moving faster, and then you open the wall and they mix together. And if you think that mixing has something to do with the second law of thermodynamics that says entropy increases and the gases diffuse into one another. It's not like the gases don't like each other and all the hot gas chooses to go to the left and all the cold gas chooses to go to the right, kind of like, children at a middle school dance might do that. They separate to the two sides of the gymnasiums. Nope, they mix together. Gases diffuse because of the second law of thermodynamics. But when you talk about gases here on this isotherm, and you wanted to get to a hotter isotherm, you want to get to a higher temperature isotherm, there's more than one way to get there. You could be isovolumeric about it or isobaric about it. Let's do isovolumeric first because that's easier. Look, it's the first law of thermodynamics. Look, it's Q equals mc delta T. Well, not exactly. Here we have Q equals nc delta T. Close enough to make us happy, and there we have the specific heat capacity of an ideal gas, the molar specific heat capacity of an ideal gas at constant volume. Key thing there, at constant volume. And enough of that. Let's do the same thing, only let's do it this way. When I say the same thing, I mean we're taking this gas from a lower temperature to a higher temperature this time. However, we're doing it isobarically. Isobarically, it's the same sort of thing, only different, because this time we have a delta W. Now, the delta W has to be negative. We are increasing in volume, so the delta W is negative, and we're looking there, and we have, I see it, we have PV equals nRT. In this derivation here, PV equals nRT, and Q equals mc delta T, or Q equals nc delta T, together at last, and we're good, and we're happy, and we can end by observing that the molar specific heat capacity at a constant pressure is greater than the molar specific heat capacity at a constant volume because it takes more energy to raise the temperature of a gas if you allow that gas to expand. This is because The gas, as you allow it to expand, the gas is doing work against the environment and not just getting hotter.